There are moments in human history when we look up at the cosmos and realize we've been wrong about almost everything. The James Webb Space Telescope has delivered one of those moments. And what it's showing us isn't just surprising. It's fundamentally rewriting the rulebook of cosmic evolution. Picture this: you're standing at the edge of a vast ocean in complete darkness. You've spent your entire life building theories about what lies beneath those black waters, constructing elaborate models based on ripples and echoes. Then someone hands you a flashlight so powerful it pierces straight to the ocean floor. And what you see down there doesn't match a single prediction you've ever made. That's where we are right now with James Webb. We turned on the flashlight, and the universe we're seeing is not the universe we expected. Let's be clear about what James Webb actually is. This isn't just a bigger Hubble. This is a time machine operating on a scale that would make science fiction writers blush. Positioned nearly 1 million miles from Earth at a gravitational sweet spot called Lagrange Point 2, this telescope is essentially looking backward through time itself. Every photon it captures has been traveling through space for billions of years, carrying information from epochs so ancient that the universe itself was practically a newborn. We're talking about light that began its journey when the cosmos was only a few 100 million years old, when the first stars were just beginning to ignite, when galaxies were nothing more than cosmic whispers in the darkness. The engineering behind this instrument borders on the miraculous. Imagine building something with a mirror so precise that if you scaled it up to the size of the United States, the largest imperfection would be only a few inches tall. Now imagine that this mirror has to unfold itself in space like cosmic origami, perfectly aligning 18 separate hexagonal segments into a single coherent surface measuring over 21 feet across. Then add a sun shield the size of a tennis court, composed of 5 layers thinner than a human hair, each one precisely separated to create a temperature differential of hundreds of degrees. On one side, the sun-facing side, temperatures soar to about 230 degrees Fahrenheit. On the other side, where the instruments live, it's nearly minus 400 degrees Fahrenheit. This temperature control isn't a luxury. It's absolutely essential because James Webb observes in infrared, detecting the heat signatures of ancient galaxies, and any warmth from the telescope itself would blind its incredibly sensitive instruments. But here's where it gets truly mind-bending. James Webb isn't just looking at distant galaxies. It's observing them at a time when they shouldn't exist. Not according to our models, anyway. When astronomers first pointed this technological marvel at the deep cosmos, they expected to see primitive, small, chaotic collections of stars. Baby galaxies stumbling through their formative years. What they found instead were massive, mature, beautifully structured spiral galaxies that looked like they'd been around for billions of years. Except the universe itself was barely 500 million years old at that point. Think about what this means. Our entire understanding of galaxy formation is built on a timeline. In the Standard Model, the universe starts with the Big Bang, then goes through a period called the Dark Ages when matter is just hydrogen and helium floating in darkness. Slowly, over hundreds of millions of years, gravity pulls this material together. The first stars form. These are massive, short-lived stars that explode as supernovas, seeding the cosmos with heavier elements. Then, gradually, over vast stretches of time, these materials coalesce into galaxies. Small galaxies merge into bigger ones. Chaos slowly gives way to structure. This process is supposed to take billions of years. It's a slow cosmic dance, methodical and predictable. James Webb is showing us galaxies that look like they skipped several billion years of evolution. They're too big, too organized, too mature for their age. It's like expecting to find a newborn baby and instead discovering a full-grown adult with a PhD and a mortgage. The universe, it seems, was far more precocious than we ever imagined. One of the most shocking discoveries came in the form of a galaxy designated Glass Z13. When astronomers calculated how far away this galaxy was based on its light signature, they determined it existed just 300 million years after the Big Bang. 300 million years sounds like a long time until you realize the universe is 13.8 billion years old. In cosmic terms, this galaxy appeared in the first 2% of universal history. And it's not alone. Webb has found dozens of these impossibly early massive galaxies, each one a contradiction wrapped in starlight. The implications cascade outward like ripples in space-time. If galaxies formed this quickly, then our understanding of dark matter, the invisible scaffolding that supposedly holds galaxies together, might need revision. Our models of how stars form, how quickly they can accumulate, how efficiently gas can cool and collapse into stellar nurseries, all of these carefully constructed theories are suddenly on shaky ground. We're not talking about small adjustments to the equations. We're talking about fundamental assumptions that might be wrong. Consider the problem of metallicity. In astronomy, anything heavier than hydrogen and helium is called a metal. These metals are forged in the cores of stars and scattered across space when those stars explode. The first generation of stars, called population 3 stars, contain no metals at all because they formed from the pristine material of the early universe. Subsequent generations of stars incorporated these metals, becoming progressively more metal-rich over time. This is how we date stellar populations. Low metallicity means old stars. High metallicity means young stars. It's a cosmic clock that's worked reliably for decades. Except James Webb is finding galaxies in the early universe with metallicity levels that shouldn't exist yet. These ancient galaxies contain elements that require multiple generations of stellar evolution to produce. But there hasn't been enough time for multiple generations. It's as if someone planted a fully grown oak tree in soil that was laid down yesterday. The timeline doesn't work. Either stars formed and died far more rapidly than we thought possible, or there's some mechanism for creating heavy elements that we don't understand at all. Then there's the issue of supermassive black holes. These gravitational monsters, millions or billions of times the mass of our Sun, sit at the centers of most large galaxies. We've known about them for years. What we didn't know is that they existed in the very early universe. James Webb has detected black holes with masses exceeding 1 billion suns in galaxies that formed less than 1 billion years after the Big Bang. This discovery has astronomers genuinely puzzled because black holes grow by consuming matter, and that process takes time. A lot of time. There are theoretical limits to how fast a black hole can grow, determined by the physics of accretion and radiation pressure. When matter falls into a black hole, it heats up and emits enormous amounts of radiation. This radiation pushes outward, creating a kind of pressure that limits how much additional matter can fall in. It's a self-regulating process called the Eddington limit. To grow 1 billion solar mass black hole in less than 1 billion years while respecting this limit requires nearly continuous feeding at maximum efficiency. It's theoretically possible, but it requires perfect conditions sustained over cosmic timescales. Finding not just one but multiple such black holes suggests either incredible luck or, more likely, that our understanding of black hole formation is incomplete. Some astronomers have proposed that these supermassive black holes didn't grow from stellar mass seeds. Instead, they might have formed directly from the collapse of massive gas clouds in the early universe, starting out already weighing thousands or tens of thousands of solar masses. These hypothetical objects are called direct collapse black holes, and until James Webb, they were purely theoretical. Now they might be necessary to explain what we're seeing. But let's zoom out for a moment and consider what all of these discoveries have in common. They all point to the same unsettling conclusion: the early universe was far more dynamic, far more efficient, and far more complex than our theories predicted. It's as if nature found shortcuts we didn't know existed. Processes we thought took billions of years happened in mere hundreds of millions. Structures we thought required countless generations of building and merging appeared almost fully formed. This raises a profound question: what else are we wrong about? If our models of the early universe are this far off, what does that mean for our understanding of dark energy, dark matter, cosmic inflation, and all the other theoretical constructs we've built to explain the cosmos? Science progresses by making predictions and testing them against reality. When reality contradicts your predictions this dramatically, you don't just tweak the numbers. You reconsider the foundations. James Webb has also given us unprecedented views of stellar nurseries, the vast clouds of gas and dust where new stars are born. The Carina Nebula, a star-forming region about 7,600 light-years from Earth, has been photographed before by Hubble and other telescopes. but Webb's infrared vision can peer through the obscuring dust that visible light can't penetrate. What it revealed looks like a cosmic landscape of mountains and valleys, with towering pillars of gas illuminated from within by the fierce radiation of newborn stars. These aren't just pretty pictures. They're scientific gold mines. By observing these regions in infrared, astronomers can watch stars being born in real time, cosmically speaking. They can see protostars still wrapped in their natal cocoons, jets of material being blasted into space at incredible speeds, and shock waves from stellar winds sculpting the surrounding gas. Each observation adds detail to our understanding of how stars form, how planetary systems emerge, and ultimately how the raw materials for life are distributed across the galaxy. One particularly stunning discovery involved brown dwarfs, objects too massive to be planets, but not quite massive enough to sustain hydrogen fusion and become true stars. These failed stars have been difficult to study because they're faint and cool. But James Webb's infrared sensitivity makes them visible in ways they've never been before. Astronomers have found brown dwarfs with masses as low as a few times that of Jupiter, blurring the line between planet and star. Some of these objects show evidence of weather patterns, cloud formations, and complex atmospheric chemistry. They're like laboratories for studying planetary atmospheres under extreme conditions. The telescope has also revolutionized our study of exoplanets, worlds orbiting distant stars. By observing these planets as they pass in front of their host stars, Webb can analyze the starlight filtering through their atmospheres. Different molecules absorb different wavelengths of light, creating a unique spectral fingerprint. This technique, called transmission spectroscopy, allows us to determine the atmospheric composition of planets dozens or hundreds of light years away. One of Webb's first exoplanet targets was WASP 96b, a gas giant about 1,150 light-years from Earth. The spectrum Webb captured showed clear evidence of water vapor, along with signatures of clouds and haze. But it's the smaller, rocky planets that really capture the imagination. These are the worlds that might harbor life. Webb has observed several such planets, including those in the TRAPPIST-1 system, a collection of 7 Earth-sized worlds orbiting a cool red dwarf star just 40 light-years away. The TRAPPIST-1 system is particularly intriguing because 3 of its planets orbit in the habitable zone, the region where temperatures might allow liquid water to exist on the surface. Early observations by Webb suggest that at least some of these planets have atmospheres, though the exact composition remains under investigation. What's remarkable is that we're now at a point where we can not only detect these worlds but also study their atmospheres in detail, searching for biosignatures, chemical indicators that might suggest the presence of life. Imagine that for a moment. We're using a telescope to analyze the air on planets orbiting other stars, looking for molecules like oxygen, methane, or phosphine in combinations that might indicate biological activity. This is the kind of science that was pure fantasy just a generation ago. And we're doing it. Right now. The question of whether we're alone in the universe is transitioning from philosophy to observational science. But let's return to those impossible galaxies in the early universe because there's another layer to this story that's even more perplexing. Some of these ancient galaxies aren't just mature. They're red. Now, in astronomy, color tells us a lot about a galaxy's stellar population. Blue galaxies are filled with young, hot, massive stars that burn bright and die fast. Red galaxies, on the other hand, are dominated by older, cooler stars. They're the cosmic retirees, galaxies that have stopped forming new stars and are coasting on the remnants of past generations. Finding red galaxies in the early universe is like finding a retirement community in a newly founded town. It shouldn't exist yet. For a galaxy to become red, it needs to have gone through its star-forming phase, exhausted its gas supply or had that gas somehow removed, and then aged for billions of years as its massive blue stars die off and only the long-lived red stars remain. This process is supposed to take a significant fraction of the universe's lifetime. Yet James Webb is finding red, dead galaxies when the universe was less than 1 billion years old. The term astronomers use for this phenomenon is quenching. Something has quenched star formation in these galaxies far earlier than should be possible. The question is, what? There are several mechanisms that can shut down star formation. Supermassive black holes at galactic centers can blast out powerful jets and winds that blow away the gas needed to make new stars. Galaxy mergers can heat gas to temperatures where it can no longer cool and collapse. The intense radiation from the first generation of massive stars might have played a role. But none of these processes work fast enough to explain what Webb is seeing. Some astronomers have proposed that these early red galaxies might be the result of an incredibly rapid initial burst of star formation that consumed all available gas in just a few 100 million years. It would require star formation rates far exceeding anything we observe in the modern universe, but perhaps the conditions in the early cosmos were uniquely suited for such explosive growth. Others suggest that we might be witnessing the effects of dark matter physics we don't yet understand, or that the interplay between galaxies and their surrounding environment was far more efficient at removing gas than current models predict. What's particularly troubling for theorists is that these discoveries aren't isolated anomalies. Webb is finding these problematic galaxies everywhere it looks. This isn't a matter of one or two weird objects that can be explained away as flukes or measurement errors. We're talking about a fundamental mismatch between theory and observation across the board. It's the kind of situation that makes scientists both excited and nervous. Excited because we're clearly on the verge of new discoveries. Nervous because it means our cherished models might be seriously flawed. Let's talk about another Webb discovery that's shaking up cosmology: the universe's expansion rate. For decades, astronomers have been trying to pin down exactly how fast the universe is expanding. This number, called the Hubble constant, is fundamental to cosmology. It tells us the age of the universe, its size, and its ultimate fate. The problem is that different methods for measuring the Hubble constant give different answers, and that discrepancy has only grown more pronounced over time. One method involves observing type I supernovas, stellar explosions that have a known intrinsic brightness. By comparing how bright they appear to how bright they should be, astronomers can calculate their distance. By measuring their redshift, which tells us how fast they're moving away, we can determine the expansion rate. This method gives a Hubble constant of about 73 km per second per megaparsec. Another method uses the cosmic microwave background, the afterglow of the Big Bang itself. By analyzing tiny temperature fluctuations in this ancient light, cosmologists can extrapolate forward and calculate what the expansion rate should be today. This method gives a Hubble constant of about 67 km per second per megaparsec. 6 km per second per megaparsec might not sound like much, but in cosmology, it's a chasm. These two methods should agree if our understanding of cosmic evolution is correct. The fact that they don't is called the Hubble tension, and it's one of the biggest unsolved problems in modern astrophysics. Either one of the measurement methods is wrong, or there's new physics we don't understand affecting how the universe expands. James Webb has entered this debate by providing the most precise measurements yet of Cepheid variable stars, pulsating stars whose brightness varies in a predictable pattern related to their intrinsic luminosity. These stars are cosmic yardsticks, and they're crucial for calibrating the supernova distance scale. Webb's observations have confirmed the supernova-based measurements with unprecedented precision, solidifying the tension. The discrepancy is real, and it's not going away. What could explain this? One possibility is that dark energy, the mysterious force accelerating the universe's expansion, behaves differently than we thought. Maybe it's not a constant but changes over time. Another possibility involves dark matter, the invisible substance that makes up most of the matter in the universe. Perhaps dark matter interacts with ordinary matter or radiation in ways we haven't accounted for. Or maybe the early universe went through additional phases of rapid expansion beyond the initial inflationary period. Each of these explanations requires new physics, and that's both thrilling and daunting. Webb has also been studying some of the universe's most extreme objects, quasars. These are supermassive black holes actively feeding on surrounding material, shining so brightly they outshine entire galaxies. The most distant quasars Webb has observed are more than 13 billion light-years away, meaning we're seeing them as they were less than a billion years after the Big Bang. And they're enormous, with black holes weighing billions of solar masses. The existence of these massive black holes so early creates the same timeline problem we discussed before, but it's even more acute with quasars because we can study them in such detail. Webb can measure the spectra of quasars, analyzing the light absorbed by gas clouds between us and the quasar. This technique reveals the chemical composition of the early universe, showing us which elements were present and in what quantities. It's like taking a census of the periodic table across cosmic time. One surprising finding is that the early universe was already enriched with heavy elements far more than expected. Carbon, oxygen, silicon, iron, all present in quantities that require significant stellar processing. This means that large numbers of massive stars must have formed, lived, and died in the first few 100 million years after the Big Bang, churning out heavy elements at a prodigious rate. Once again, we're seeing evidence that the early universe was far more active and productive than our models suggest. Now let's venture into even stranger territory: gravitational lensing. This is a phenomenon where the gravity of a massive object, like a galaxy cluster, bends the path of light from objects behind it, creating distorted, magnified, and sometimes multiple images. Einstein predicted this effect, and it's been observed countless times. But James Webb is using gravitational lensing to see objects that would otherwise be completely invisible. Some of the most distant galaxies Webb has discovered were only detectable because a massive galaxy cluster in the foreground acted as a natural telescope, magnifying the light from these ancient galaxies by factors of 10 or even 100. Without this cosmic assist, they'd be far too faint to see. It's a beautiful synergy of natural phenomena and human ingenuity. But here's where it gets really interesting. The extreme magnification allows astronomers to study these distant galaxies in unprecedented detail. We're not just detecting them, we're resolving their structure, seeing spiral arms, star-forming regions, and even individual star clusters in galaxies billions of light years away. This level of detail is giving us insights into how galaxies assembled their mass, how they interacted with their environments, and how the first generations of stars influenced galactic evolution. One particularly remarkable lensed galaxy, nicknamed the Cosmic Seahorse, has been magnified so much that astronomers can see features less than 300 light-years across in a galaxy that existed when the universe was only a couple of billion years old. That's like being able to distinguish individual neighborhoods in a city from 1,000 miles away. The information density in these observations is staggering. Webb has also turned its gaze toward our own solar system, and even there, it's making surprising discoveries. Observations of Jupiter revealed auroras at both poles, vast storms in the atmosphere, and details of the planet's ring system that were previously invisible. The moons of Jupiter and Saturn, worlds with subsurface oceans that might harbor life, are being studied with new precision. Europa, Jupiter's ice-covered moon, shows surface features that suggest active geology and potential plumes of water vapor erupting from cracks in the ice. These plumes, if they exist, could be sampled by future missions, giving us direct access to the ocean beneath without having to drill through miles of ice. Saturn's moon Enceladus, which also has a subsurface ocean and known geysers shooting water into space, is another prime target. Webb has detected not just water but also organic molecules in these plumes, adding to the evidence that Enceladus might have the right ingredients for life. The fact that we can study the chemical composition of water from an alien ocean, even if it's within our own solar system, is remarkable. Mars has also been observed by Webb, revealing atmospheric dynamics and seasonal changes with clarity that complements data from rovers and orbiters. The telescope detected variations in carbon dioxide ice at the polar caps and tracked dust storms as they developed. While Mars is well studied, Webb's unique perspective adds another layer to our understanding of Martian climate and weather. But let's return to the deeper implications of what James Webb is revealing. There's a philosophical dimension to all of this that's worth considering. For the entirety of human history, our understanding of the universe has been limited by the tools we had to observe it. Ancient astronomers saw patterns in the sky and constructed mythologies. Galileo's telescope revealed moons orbiting Jupiter and phases of Venus, shattering the Earth-centered model of the cosmos. Edwin Hubble's observations showed that the universe was expanding, giving birth to the Big Bang theory. Each leap in observational capability has forced us to revise our understanding, and each revision has made the universe stranger and more wonderful. James Webb represents another such leap, perhaps the most significant since Hubble itself. What's humbling is the realization that despite all our progress, despite our sophisticated models and powerful theories, the universe still has the capacity to surprise us. We thought we understood galaxy formation. We were wrong, or at least incomplete. We thought we knew the timeline of cosmic evolution. We're revising it. We believed our measurements of the universe's expansion rate were converging. They're diverging. This is how science progresses. Not through steady accumulation of confirmatory evidence, but through moments of disruption when nature refuses to behave according to our expectations. These are the moments that lead to breakthroughs. Einstein didn't develop relativity by confirming Newtonian mechanics. He developed it by addressing anomalies that Newtonian mechanics couldn't explain. Quantum mechanics arose from the failure of classical physics to explain atomic spectra and blackbody radiation. We're potentially at another such moment. The discoveries James Webb is making aren't just filling in details. They're challenging fundamental assumptions. And that's exactly what you want from a revolutionary scientific instrument. If Webb had simply confirmed everything we already believed, it would be a technological triumph, but a scientific disappointment. Instead, it's doing what the best observatories do, forcing us to think harder, question deeper, and imagine more boldly. Consider the broader context of our cosmic ignorance. We know that ordinary matter, the stuff that makes up stars, planets, and people, constitutes only about 5% of the universe's total mass energy content. About 27% is dark matter, which we can detect through its gravitational effects but have never directly observed. And the remaining 68% is dark energy, an even more mysterious component that seems to be accelerating the universe's expansion. We've built elaborate theories around these concepts, but the truth is we don't really know what dark matter and dark energy are. We've named our ignorance and built models around it, but we haven't solved the puzzle. James Webb isn't directly detecting dark matter or dark energy, but its observations are constraining models and forcing refinements. The distribution of galaxies in the early universe tells us about the structure of dark matter at that time. The expansion rate measurements feed into our understanding of dark energy. Every observation is a piece of a vast puzzle, and Webb is providing pieces we didn't even know were missing. There's also the tantalizing possibility that some of what Webb is seeing might hint at physics beyond the standard model. The standard model of particle physics has been incredibly successful, predicting the existence of particles like the Higgs boson decades before they were discovered. But it's incomplete. It doesn't include gravity. It doesn't explain dark matter. It doesn't account for the matter-antimatter asymmetry in the universe. Physicists know there must be new physics beyond the standard model, but discovering what that physics is requires either high-energy particle colliders or observations of extreme cosmic phenomena. James Webb provides the latter. For instance, if the early universe produced primordial black holes, theoretical objects formed from density fluctuations shortly after the Big Bang, they might account for some fraction of dark matter. Webb's ability to detect and characterize black holes in the early universe could provide evidence for or against this hypothesis. Similarly, if there are additional particles or fields that played a role in the early universe, their effects might be visible in the cosmic microwave background or in the distribution of early galaxies. We're also using Webb to study cosmic reionization, a pivotal event in cosmic history when the first stars and galaxies produced enough ultraviolet light to ionize the neutral hydrogen that filled the universe. Before reionization, the universe was opaque to most light, a kind of cosmic fog. After reionization, the universe became transparent, allowing light to travel freely across space. Understanding when and how this transition occurred tells us about the nature of the first stars and the energy they produced. Webb's observations are revealing that reionization was a complex, patchy process that happened over hundreds of millions of years. Some regions of the universe cleared earlier than others, creating bubbles of ionized gas around the first galaxies. These bubbles eventually overlapped and merged, completing the reionization process. By mapping these bubbles and measuring their sizes, astronomers can infer the properties of the galaxies responsible for reionization, even if those galaxies themselves are too faint to detect directly. Another area where Webb is making waves is in the study of stellar populations within galaxies. By taking spectra of galaxies, astronomers can determine not just the total mass of stars but also the distribution of stellar ages and metallicities. This is like taking a census of a galaxy's stellar citizens, figuring out how many are young versus old, rich in metals versus metal poor. This information reveals the galaxy's star formation history, telling us when it formed most of its stars and how that rate has changed over time. What Webb is finding is that many galaxies in the early universe had remarkably complex star formation histories. They didn't just form stars at a steady rate. Instead, they went through bursts and lulls, periods of intense activity followed by relative quiescence. This bursty star formation might be driven by interactions with other galaxies, inflows of fresh gas, or feedback from supernovas and black holes. Each burst leaves its mark on the galaxy's stellar population, creating a kind of archaeological record that Webb can read. There's also growing evidence that the very first stars, the population 3 stars we mentioned earlier, might have been more massive than we thought. These stars formed from pristine hydrogen and helium, with no heavy elements to help cool the gas. As a result, they might have been hundreds of times the mass of the Sun, incredibly hot and short-lived. When they exploded as supernovas, or perhaps as even more energetic hypernovas, they would have seeded the surrounding space with the first heavy elements, setting the stage for subsequent generations of stars. Detecting these first stars directly is extraordinarily difficult because they were rare and short-lived, winking out of existence within a few million years. But Webb might be able to see their signatures indirectly, either through the chemical fingerprints they left behind or by detecting the unusual supernovas they produced. Some models predict that the very most massive population 3 stars collapsed directly into black holes without exploding, while others might have produced parinstability supernovas, a type of explosion so energetic it completely disrupts the star, leaving no remnant behind. Webb's spectroscopic capabilities might allow us to distinguish between these scenarios. Let's talk about cosmic dust for a moment, because it's playing a surprising role in Webb's discoveries. Dust, composed of tiny grains of silicates and carbon, absorbs visible and ultraviolet light but re-emits it as infrared radiation. This means that dusty regions of the universe, which are opaque to optical telescopes like Hubble, are transparent to James Webb. This is one reason Webb can see through the dust clouds in stellar nurseries and reveal the baby stars within. But dust also tells us about stellar evolution because it's produced in the atmospheres of dying stars and in supernova explosions. The amount and composition of dust in a galaxy reflects its history of star formation and stellar death. Webb has detected significant amounts of dust in some of the earliest galaxies, which is surprising because dust production requires time. Stars need to form, evolve, and die before they can produce substantial quantities of dust. Finding dusty galaxies in the early universe suggests, once again, that stellar evolution proceeded faster than expected. There's also the question of how dust grains themselves form. In the atmospheres of cool, evolved stars like red giants, atoms can condense into small clusters and eventually into grains. In supernova ejecta, rapid cooling can also lead to dust formation. But the details of these processes are complex and depend on temperature, density, and chemical composition. Webb's observations of dust in various environments are helping to refine our models of dust formation and evolution, which in turn affects our understanding of planet formation because dust grains are the building blocks of planets. Speaking of planets, let's delve deeper into what Webb is revealing about planetary systems. The telescope has observed protoplanetary disks, the swirling clouds of gas and dust around young stars where planets are forming. These disks are structured in complex ways, with gaps and rings that indicate the presence of forming planets. By observing these disks in infrared, Webb can see through the outer layers and probe the midplane where planets are actually assembling. One fascinating discovery involves the chemistry of these disks. Webb has detected a variety of organic molecules, including water, methane, carbon dioxide, and even more complex compounds like acetylene and benzene. These molecules are the raw materials for planets and potentially for life. The fact that they're abundant in protoplanetary disks means that the chemical ingredients for life are commonplace in the universe. Whether those ingredients actually lead to life is a separate question, but at least the raw materials are there. Webb has also observed debris disks, systems where planets have already formed and the remaining dust and debris are grinding down through collisions. These are analogous to the asteroid belt and Kuiper belt in our own solar system. By studying debris disks around other stars, astronomers can infer the architectures of those planetary systems, figuring out where giant planets likely orbit based on gaps in the debris distribution. One particularly exciting area of research involves studying the atmospheres of hot Jupiters, gas giant planets that orbit extremely close to their host stars. These planets are tidally locked, with one side perpetually facing the star and the other side in permanent darkness. Webb can observe how heat is transported from the day's side to the night side, revealing wind patterns and atmospheric circulation. Some hot Jupiters show evidence of high-altitude clouds, possibly made of exotic minerals like corundum or perovskite, that form on the night side and then rain down on the day's side. The level of detail Webb is achieving in exoplanet studies is opening up the field of comparative planetology beyond our solar system. We can now compare atmospheric properties, thermal structures, and chemical compositions across a variety of planets, looking for patterns and trends. Do all hot Jupiters have stratospheres? How does atmospheric composition vary with planet mass and stellar type? Are there universal processes that govern planetary atmospheres, or is every world unique? Webb is providing the data to answer these questions. Now, let's consider the future. James Webb is designed to operate for at least 10 years, possibly longer if its fuel reserves for maintaining its orbit last. During that time, it will continue to observe the universe across a wide range of wavelengths and targets. Astronomers have already proposed thousands of observing programs, far more than Webb can possibly execute. Every hour of telescope time is precious, carefully allocated to maximize scientific return. But Webb isn't working alone. It's part of a broader ecosystem of observatories, each with its own strengths. Ground-based telescopes like the European Extremely Large Telescope and the 30-meter telescope, currently under construction, will have larger mirrors and can study brighter objects in greater detail. Space missions like the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission are designed for wide-field surveys, mapping large swaths of the sky to understand the large-scale structure of the universe. Webb's role is to provide the deep, detailed observations that complement these broader surveys. There are also plans for future infrared missions that could succeed Webb, though they're still in the conceptual stage. These might include even larger space telescopes, interferometric arrays that combine light from multiple spacecraft, or specialized instruments designed to study specific phenomena like gravitational waves or cosmic rays. Each generation of instruments builds on the discoveries of the previous one, asking new questions and pushing the boundaries of what's possible. But in the here and now, James Webb is rewriting textbooks. Literally. Astronomy textbooks published just a few years ago are already outdated in several key areas. The chapters on galaxy formation, the early universe, and even the Hubble constant are being revised as we speak. This is the nature of science, it's never finished. Every answer raises new questions. Every discovery opens new avenues of investigation. What's remarkable is how quickly these discoveries are happening. Webb has only been operational since mid-2022, and in that relatively short time, it's already produced a flood of groundbreaking results. Part of this is due to the telescope's capabilities, but part of it is also due to the way modern astronomy works. Data from Webb is made publicly available after a relatively short proprietary period, allowing astronomers around the world to analyze it. Machine learning algorithms help sift through vast datasets, identifying interesting objects for further study. International collaborations bring together experts from different fields, combining their knowledge to tackle complex problems. The pace of discovery is exhilarating, but it's also a reminder of how much we still don't know. The universe is a vast, complex place, and even with our most advanced instruments, we're only scratching the surface. James Webb is showing us the universe in a new light, literally, and what we're seeing is both familiar and alien. Familiar because the laws of physics still apply, because gravity still pulls matter together, because stars still shine. Alien because the details are so different from what we expected, because the timeline is compressed, because nature found ways we hadn't imagined. There's a humility in this that's important to embrace. Science isn't about having all the answers. It's about asking better questions, building better tools, and being willing to revise your understanding when the evidence demands it. James Webb is demanding that we revise a lot. And that's not a failure of our previous theories. It's a success of the scientific method. We built a telescope to test our ideas, and the telescope told us we were wrong in interesting ways. Now we get to figure out why. Let's consider some of the specific targets Webb has observed that are emblematic of its mission. The Southern Ring Nebula, a planetary nebula about 2,500 light-years away, was one of Webb's early showcase images. A planetary nebula has nothing to do with planets. It's the glowing shell of gas ejected by a dying sun-like star. What Webb revealed was astonishing. Not just one star at the center but two, a binary system. The nebula's intricate structure, with shells within shells and delicate filaments, is the result of these two stars' complex interaction over thousands of years. The dying star shed its outer layers, and its companion star's gravity shaped the outflow, creating the beautiful, complex structure we see. But Webb didn't just take pretty pictures. Its spectrographs analyzed the chemical composition of the gas, revealing the presence of molecules that were previously undetected. This tells us about the nuclear reactions that occurred inside the star before it died, about the elements it created and expelled into space. These elements, including carbon, nitrogen, and oxygen, are the building blocks of life. Every atom in your body heavier than hydrogen was forged in the core of a star and dispersed across space in events like this. Webb is showing us the cosmic recycling process in exquisite detail. Another iconic target is Stephan's quintet, a group of 5 galaxies that appear close together in the sky. 4 of them are actually interacting, locked in a slow-motion gravitational dance that's tearing them apart and triggering massive bursts of star formation. The 5th galaxy is a foreground object, not physically associated with the others. Webb's image of Stephan's quintet revealed shock waves as gas from one galaxy slams into another, regions of intense star formation glowing in infrared, and the complex interplay of gravity and hydrodynamics as these galaxies merge. Galaxy interactions like this are thought to be a major driver of galactic evolution. When galaxies collide, their gas clouds smash together, compressing and triggering star formation. Over time, the galaxies can merge completely, forming a single larger galaxy. Our own Milky Way is on a collision course with the Andromeda Galaxy, though the impact won't occur for another 4 billion years. Webb's observations of merging galaxies in the present-day universe give us a preview of what might happen when Milky Way and Andromeda eventually meet. Webb has also observed the Pillars of Creation, one of Hubble's most famous images. Located in the Eagle Nebula about 6,500 light-years away, the pillars are towering columns of gas and dust where new stars are forming. Hubble's visible light image showed the pillars backlit by stars, creating a dramatic silhouette. Webb's infrared view, however, revealed the stars forming inside the pillars, previously hidden by the dust. Hundreds of newly formed stars, many still surrounded by dusty disks, became visible. It's a stark illustration of the complementary nature of different wavelengths. Visible light shows you the surface. Infrared shows you what's inside. These observations aren't just aesthetically pleasing, they're scientifically valuable. By counting the number of young stars and measuring their properties, astronomers can determine the star formation rate in the Eagle Nebula and compare it to other star-forming regions. This helps us understand what conditions favor star formation and how efficiently gas is converted into stars under different circumstances. Webb has also turned its attention to some of the universe's most violent events, supernovas. These stellar explosions are among the brightest events in the cosmos, briefly outshining entire galaxies. Supernovas are crucial for several reasons. They're the primary mechanism for distributing heavy elements across space. They can trigger star formation in nearby clouds by compressing them with their shock waves. and certain types of supernovas, the type Ia supernovas we mentioned earlier, serve as cosmic distance markers. By observing supernovas in the infrared, Webb can peer through the dust and debris ejected by the explosion and see what's happening in the core. It can detect the radioactive isotopes produced in the explosion as they decay, releasing energy that powers the supernova's light. It can study the shock wave as it plows through surrounding material. Each supernova is a laboratory for extreme physics, where matter is heated to billions of degrees, where elements are transmuted, where neutron stars and black holes are born. Webb has also observed the remnants of ancient supernovas, expanding shells of gas that are all that remain of stars that exploded thousands of years ago. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054 AD, is a favorite target. At its center is a pulsar, a rapidly spinning neutron star that emits beams of radiation like a cosmic lighthouse. Webb's observations are revealing the detailed structure of the nebula, showing how the pulsar's wind interacts with the surrounding material, creating complex magnetic structures and accelerating particles to near light speed. Let's talk about something that might seem mundane but is actually profound: cosmic chemistry. The universe started with just hydrogen and helium, plus trace amounts of lithium. Every other element was created inside stars or in stellar explosions. This process, called nucleosynthesis, is how the periodic table was assembled. Hydrogen fuses into helium in the cores of stars. Helium fuses into carbon and oxygen. In the most massive stars, the chain continues up to iron. Elements heavier than iron are produced in supernova explosions or in the collisions of neutron stars. Webb is studying this chemical evolution in unprecedented detail. By observing stars and gas clouds at different distances, and therefore at different times in cosmic history, we can track how the abundance of elements has changed over billions of years. In the early universe, there were only trace amounts of anything beyond hydrogen and helium. Today, about 2% of the mass in the universe is in heavier elements, a number that seems small but represents a tremendous amount of material. Every rocky planet, every living organism, every molecule in your body is made from that 2%. What Webb is finding is that the chemical enrichment of the universe happened faster than expected, especially in the first billion years. This ties back to those early massive galaxies we discussed. If galaxies formed quickly and produced stars rapidly, then the chemical enrichment would also proceed rapidly. It's all connected: the rate of star formation, the distribution of galaxy masses, the chemical composition of gas and stars, the formation of planets, and ultimately the potential for life. Another area where Webb is making contributions is in the study of star clusters. These are groups of stars that form together from the same cloud of gas and are bound together by gravity. Some clusters are young, only a few million years old, with bright, hot stars. Others are ancient globular clusters, containing hundreds of thousands of stars that are more than 10 billion years old. Globular clusters are among the oldest objects in the universe, forming in the early stages of galaxy formation. Webb can resolve individual stars and globular clusters, even in distant galaxies. This allows astronomers to study the properties of ancient stars, determining their ages, masses, and chemical compositions. By comparing globular clusters in different galaxies, we can learn about the conditions under which they formed and how galaxies themselves assembled. Some theories suggest that galaxies formed through the merger of smaller building blocks, and globular clusters might be the surviving cores of those building blocks. There's also the fascinating topic of gravitational waves, ripples in space-time caused by the acceleration of massive objects. While Webb doesn't detect gravitational waves directly, it can observe the electromagnetic counterparts of gravitational wave events. For instance, when two neutron stars collide, they produce both gravitational waves and a brilliant flash of light called a kilonova. Webb can observe the kilonova, analyzing its spectrum to determine what elements were produced in the collision. These collisions are thought to be a major source of heavy elements like gold, platinum, and uranium. The first observed neutron star merger, detected in 2017 by gravitational wave observatories and followed up by dozens of telescopes around the world, confirmed that these events do indeed produce heavy elements. Webb's superior infrared sensitivity means it can detect kilonovas at much greater distances than previous telescopes, allowing us to study these rare events in more detail and in a wider range of environments. Let's not forget about the role of citizen scientists and public engagement in Webb's mission. Many of the stunning images produced by Webb are not just for scientists, but for everyone. They inspire wonder, spark curiosity, and remind us of our place in the cosmos. Astronomy has always had a unique ability to captivate people's imaginations, and Webb is continuing that tradition. The images are shared widely on social media, featured in documentaries, and used in educational settings around the world. But beyond the images, there's also the data. Much of Webb's data is publicly accessible, and citizen science projects allow anyone with an internet connection to contribute to real research. People can help classify galaxies, identify unusual objects, or search for exoplanets in datasets. This democratization of science is a relatively recent development, enabled by the internet and by the sheer volume of data modern telescopes produce. Professional astronomers can't analyze it all alone, they need help. And in return, citizen scientists get to participate in the process of discovery. Now, let's address a question that often comes up: what's next for cosmology? If James Webb is challenging our models of galaxy formation and the early universe, what do we do about it? The answer is multifaceted. First, we need more data. Webb is still relatively new, and many of its most ambitious programs are ongoing. As more observations accumulate, patterns will become clearer. Some anomalies might resolve themselves as we better understand the telescope's capabilities and potential systematic errors. Others will solidify as genuine puzzles that demand explanation. Second, we need better theoretical models. Astrophysicists are already hard at work running simulations and developing new theories to explain Webb's observations. These models need to account for the rapid formation of massive galaxies, the early appearance of supermassive black holes, the high metallicity of early stars, and all the other surprises Webb has uncovered. This work is computationally intensive, requiring some of the world's most powerful supercomputers to simulate the complex interplay of gravity, hydrodynamics, radiation, and magnetic fields over cosmic timescales. Third, we need complementary observations from other telescopes. Webb is incredibly powerful, but it doesn't do everything. Radio telescopes can observe the cold molecular gas that fuels star formation. X-ray telescopes can study the hot gas around galaxies and the energetic emissions from black holes. Ultraviolet telescopes can observe the young, hot stars that dominate star-forming galaxies. By combining data across the electromagnetic spectrum, we get a more complete picture. There's also the question of what future telescopes might be needed. Some astronomers are already proposing missions that could succeed Webb, with even larger mirrors or new capabilities. Others are focusing on improving ground-based observatories, which can be upgraded over time in ways that space telescopes cannot. Still others are developing new techniques, like adaptive optics, that can compensate for the blurring effects of Earth's atmosphere and allow ground-based telescopes to achieve space-like image quality. But perhaps the most important thing we need is a willingness to be wrong. Science advances not by clinging to cherished ideas but by following the evidence wherever it leads. If James Webb is telling us that our models of the early universe are inadequate, then we need to listen. If the Hubble tension is pointing toward new physics, we need to take it seriously. If the universe is stranger than we thought, we need to embrace that strangeness and figure out what it means. There's a famous quote often attributed to physicist Richard Feynman. "It doesn't matter how beautiful your theory is, it doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong." James Webb is the experiment. It's testing our theories against reality. And in many cases, reality is winning. That's not a failure, it's an opportunity. Consider the historical precedents. When Galileo observed the moons of Jupiter, it contradicted the prevailing belief that all celestial bodies orbited Earth. When Hubble discovered that the universe was expanding, it contradicted the belief that the universe was static and eternal. When Arno Penzias and Robert Wilson detected the cosmic microwave background, it provided strong evidence for the Big Bang, contradicting steady-state models of the universe. Each of these discoveries was initially controversial, but the evidence was overwhelming, and eventually, the scientific consensus shifted. We might be at a similar juncture now. The evidence from James Webb is accumulating, and it's pointing toward a picture of the early universe that doesn't match our expectations. The question is whether we can adjust our models to accommodate these new observations or whether we need a more fundamental rethinking of how galaxies form and evolve. One possibility that's gaining traction is that the interplay between dark matter and ordinary matter in the early universe was more complex than we thought. Dark matter provides the gravitational scaffolding for galaxies, but the details of how ordinary matter falls into these dark matter halos and forms stars depend on a host of processes: gas cooling, feedback from supernovas and black holes, magnetic fields, turbulence, and more. Perhaps these processes were more efficient in the early universe due to different conditions. Maybe the gas was able to cool and collapse faster. Maybe the first generation of stars produced more feedback, which paradoxically could have triggered additional star formation by compressing surrounding gas. Another possibility is that our understanding of dark matter itself needs revision. Most models assume dark matter is cold, meaning it moves slowly compared to the speed of light. Cold dark matter naturally forms hierarchical structures, with small clumps merging into larger ones over time. But what if dark matter is warm or has some other property we haven't accounted for? This could change the timeline and manner in which structures form, potentially allowing galaxies to assemble faster. There are even more exotic possibilities. Some physicists have proposed modifications to the theory of gravity itself, suggesting that Einstein's general relativity might need adjustments on cosmological scales. These theories, collectively known as modified gravity theories, can sometimes explain observations without invoking dark matter or dark energy. However, they face significant challenges in matching all the available data, and most physicists remain committed to general relativity. Still, James Webb's observations might provide new tests that could distinguish between general relativity and its alternatives. Let's also consider the role of feedback processes in more detail. When stars form, they don't do so quietly. Massive stars emit intense ultraviolet radiation that can ionize surrounding gas, heating it and preventing it from collapsing to form more stars. When these massive stars explode as supernovas, they inject enormous amounts of energy into their surroundings, blowing gas out of the galaxy entirely. Black holes, too, can produce powerful winds and jets that affect their host galaxies. All of these feedback processes regulate star formation, and understanding them is crucial for modeling galaxy evolution. In the early universe, feedback processes might have been even more important because galaxies were smaller and less massive, making it easier for feedback to eject gas. But at the same time, the rate of star formation was higher, so there was more feedback to begin with. It's a delicate balance, and getting the details right in simulations is challenging. Webb's observations of early galaxies, including measurements of their star formation rates, masses, and gas content, provide crucial constraints on these models. There's also the question of cosmic variance. The universe is not uniform. Even on large scales, there are regions with more galaxies and regions with fewer. If our observations of the early universe happen to be biased toward overdense regions, we might be seeing an unrepresentative sample. This could make the universe look like it forms structure faster than average. However, Webb's observations cover a significant volume of space, and the sheer number of massive early galaxies suggests that this isn't just a statistical fluke. Another intriguing aspect of Webb's mission is its study of the intergalactic medium, the diffuse gas that fills the space between galaxies. This gas is incredibly sparse, typically containing only 1 or 2 atoms per cubic meter, but it accounts for a significant fraction of the universe's ordinary matter. By observing distant quasars, whose light passes through this gas on its way to us, astronomers can study the intergalactic medium's properties. Absorption lines in the quasar's spectrum reveal the presence of various elements, allowing us to map the chemical enrichment of intergalactic space. What Webb is finding is that even the intergalactic medium in the early universe contains measurable amounts of heavy elements, suggesting that gas ejected from early galaxies enriched the space around them. This process, called galactic winds or outflows, is a key component of galaxy evolution. It redistributes elements across cosmic scales and can affect the formation of subsequent generations of galaxies. Let's take a moment to appreciate the sheer technological achievement that James Webb represents. This is a machine that operates at temperatures barely above absolute zero, in the vacuum of space, a million miles from Earth. It's controlled remotely, with commands sent via radio waves that take several seconds to travel each way. Every movement of its mirrors, every activation of its instruments, has to be planned and executed flawlessly because there's no way to send astronauts to fix it if something goes wrong. The fact that Webb has worked so well, producing stunning images and groundbreaking science right from the start, is a testament to the thousands of engineers, scientists, and technicians who designed, built, tested, and now operate this observatory. It's an international collaboration involving NASA, the European Space Agency, and the Canadian Space Agency, with contributions from institutions around the world. It's a reminder of what humanity can achieve when we work together toward a common goal. And the goal is nothing less than understanding our origins. Where did we come from? How did the universe evolve from a hot, dense state shortly after the Big Bang to the rich tapestry of galaxies, stars, and planets we see today? How did life arise on Earth, and is it likely to exist elsewhere? These are the deepest questions we can ask, and James Webb is helping us answer them. Every photon that James Webb collects has been traveling through space for billions of years, a tiny messenger carrying information about the distant past. When we analyze that light, we're reading a message written by the universe itself. The message is complex, encoded in wavelengths and intensities, in spectral lines and redshifts. But we're learning to read it, and what it's telling us is astonishing. The universe is older than we thought, in the sense that it accomplished more in its youth than we believed possible. It's larger than we can fully comprehend, with hundreds of billions of galaxies, each containing hundreds of billions of stars, many of those stars surrounded by planets. It's more dynamic than our models predicted, with galaxies forming, merging, and evolving in ways that challenge our theories. And it's more mysterious than we'd like to admit, filled with dark matter and dark energy whose true natures remain elusive. But mystery is not a roadblock, it's an invitation. Every unanswered question is an opportunity for discovery. Every anomaly is a chance to learn something new. James Webb is showing us the universe as it truly is, not as we wish it to be or as our theories predict it should be. And that's exactly what we need. As we look to the future, we can anticipate many more discoveries from Webb. The telescope is still in the early stages of its mission, with years of observations ahead. Astronomers are planning studies of everything from the formation of the first stars to the atmospheres of potentially habitable exoplanets. We'll learn more about the structure and composition of distant galaxies, about the life cycle of stars, about the complex chemistry of protoplanetary disks. We'll also likely encounter more surprises, more observations that don't fit neatly into our current frameworks. And that's a good thing. Science thrives on anomalies. They're the signposts pointing toward new understanding. Without them, we'd just be confirming what we already know, which might be satisfying but wouldn't move us forward. There's also the human element to consider. The scientists analyzing Webb's data are people with hopes, dreams, and biases. They're working in a competitive environment where publications and funding are finite resources. But they're also driven by curiosity, by a genuine desire to understand the cosmos. The best science happens when that curiosity is tempered with skepticism, when researchers challenge their own assumptions and those of their colleagues, when the community collectively works toward the truth. James Webb is a tool, an incredibly sophisticated tool, but still just a tool. What matters is how we use it, what questions we ask, and how we interpret the answers. The telescope doesn't have an agenda. It doesn't care about our theories or our reputations. It simply collects light and sends it back to Earth. What we do with that light is up to us. In a sense, every image from James Webb is a kind of time capsule. It captures a moment in the universe's history, preserved in light. The galaxies we see in Webb's deepest images no longer look the way they did when their light left them. They'd evolved, merged with other galaxies, formed new generations of stars. Some might not even exist anymore. But their light continues to travel through space, and when it reaches us, we can study it and learn about the universe as it was billions of years ago. This is one of the most profound aspects of astronomy. We're not just looking at distant places, we're looking back in time. The farther we look, the further back we see. James Webb is looking so far that it's seeing galaxies as they were when the universe was in its infancy. It's like discovering a photo album from your earliest childhood, filled with pictures you've never seen before, showing you in ways you don't remember and can barely recognize. And just as such a photo album might change your understanding of your own history, Webb's observations are changing our understanding of cosmic history. We're learning that the universe's childhood was more eventful than we realized, that galaxies grew up faster, that the processes shaping the cosmos were more vigorous and efficient. There's a philosophical question embedded in all of this. Why is the universe comprehensible at all? Why should the patterns we observe follow mathematical laws that we can discover and understand? Why should our experiments and observations yield consistent results that allow us to build theories and make predictions? These are deep questions that touch on the nature of reality itself. One answer is that the universe is comprehensible because it has to be. If the laws of physics were inconsistent or chaotic, structures like galaxies, stars, and planets couldn't form. And if those structures couldn't form, either could life or consciousness. The fact that we're here to ask these questions might imply that the universe must have a certain orderliness. This is a variant of the anthropic principle, the idea that the universe's properties are constrained by the requirement that it must be capable of supporting observers. But regardless of why the universe is comprehensible, the fact remains that it is, at least partially. We can build telescopes like James Webb, point them at the sky, and learn genuine truths about the cosmos. We can measure the properties of galaxies billions of light years away and use those measurements to refine our theories. We can predict where planets should form and then observe them. We can calculate the age of the universe and have that calculation match independent measurements. This success is remarkable and shouldn't be taken for granted. It represents millennia of human effort, from ancient astronomers tracking the motions of planets to modern scientists analyzing data from space telescopes. Each generation builds on the work of the previous one, refining techniques, correcting errors, and expanding the scope of our knowledge. James Webb is the latest chapter in this ongoing story. It's not the final chapter. There will be future telescopes, future discoveries, future revisions to our understanding. But it's a significant chapter, one that's forcing us to reconsider some of our most fundamental ideas about how the universe works. As we conclude this exploration of what James Webb has revealed, it's worth reflecting on the broader implications. We live in a remarkable time when technology allows us to probe the deepest mysteries of existence. We can see nearly to the edge of the observable universe. We can study planets around other stars. We can watch galaxies collide in slow motion. We can detect gravitational waves from merging black holes. We can even claim, with some confidence, to understand the first few moments after the Big Bang. But with each answer, new questions emerge. How did the first stars form? What is dark matter made of? Why is the universe's expansion accelerating? Are we alone in the cosmos? James Webb is helping us address some of these questions, but it's also revealing how much we still don't know. And that's perhaps the most important lesson of all. The universe is vast, ancient, and complex. Our understanding of it, impressive as it is, remains incomplete. There are phenomena we haven't discovered yet, processes we haven't imagined, connections we haven't made. The journey of scientific discovery is far from over. If anything, James Webb has shown us that we're still in the early stages. So when we look at those stunning images from James Webb, we should see more than just beautiful pictures. We should see challenges to our assumptions, invitations to think deeper, and reminders of how much there is yet to learn. We should see the universe as it truly is, a place of wonder, complexity, and endless mystery. A place that rewards curiosity with discovery and humility with wisdom. The James Webb Space Telescope looked into the unknown, and what it found challenges everything we thought we knew. But that's not a problem. It's an opportunity. An opportunity to revise our theories, to ask better questions, and to continue the greatest adventure humanity has ever undertaken, the quest to understand the cosmos and our place within it. The universe has been speaking to us since the dawn of time, and we're finally learning to listen. What James Webb is teaching us is that the conversation is just beginning, and the most profound revelations may still lie ahead, waiting for us among the stars, in the depths of space and time, where light from the beginning of everything continues its endless journey toward us, carrying secrets we've only begun to uncover. The cascade of revelations from James Webb extends into territories we barely anticipated. Consider what the telescope has revealed about cosmic magnetic fields, those invisible lines of force threading through space that shape the behavior of charged particles across galactic scales. These fields aren't just background noise, they're active players in the drama of star formation, influencing how gas clouds collapse, how matter accretes onto black holes, and how galaxies maintain their structural integrity over billions of years. Webb has detected polarized light from dust grains aligned by magnetic fields in distant star-forming regions, providing the first detailed maps of magnetic field geometry in the early universe. What's emerging is a picture of magnetic fields that were surprisingly strong and well-organized far earlier than theoretical models suggested. This challenges our understanding of how these fields originated and amplified. Did they emerge from quantum fluctuations in the first moments after the Big Bang? Were they generated by the motion of charged particles in the first stars? The answer remains elusive, but Webb is providing crucial observational constraints. There's something deeply unsettling about discovering that galactic-scale magnetic fields existed when the universe was less than 1 billion years old. These fields require sustained dynamo processes to maintain their strength, mechanisms where the motion of conducting fluids generates and amplifies magnetic fields. In galaxies today, this happens through the differential rotation of the galactic disk and the turbulent motion of gas. But in the early universe, galaxies were still assembling. They were smaller, more chaotic, less organized. How did they manage to generate coherent magnetic fields so quickly? Some astrophysicists are proposing that the first generation of massive stars produced powerful magnetized winds that seeded the intergalactic medium with magnetic fields. As galaxies formed and pulled in this magnetized material, they inherited these primordial fields. Others suggest that cosmic rays, high-energy particles accelerated by supernova shocks, played a role in amplifying weak seed fields through plasma instabilities. Webb's observations aren't definitive enough yet to distinguish between these scenarios, but they're narrowing the possibilities. Let's shift our attention to something equally perplexing: the abundance of carbon monoxide in the early universe. Carbon monoxide might seem mundane, a toxic gas we associate with incomplete combustion, but in astronomy it's a crucial tracer of molecular gas. Molecular gas is where stars form, so tracking carbon monoxide tells us where star formation is happening and how much fuel is available. Webb has detected carbon monoxide in galaxies at redshifts exceeding 10, meaning we're seeing them less than 500 million years after the Big Bang. The problem is that carbon monoxide requires both carbon and oxygen, elements that should be relatively scarce in the early universe. Carbon is produced in stars through the triple alpha process, where 3 helium nuclei fuse into carbon. Oxygen comes from even more massive stars that can burn helium into heavier elements. Both elements are then distributed by supernova explosions. For carbon monoxide to be abundant in these early galaxies, there must have been a rapid cycle of star formation and stellar death, enriching the interstellar medium with heavy elements in just a few 100 million years. What makes this even more remarkable is that carbon monoxide molecules are fragile. Ultraviolet radiation easily breaks the bonds between carbon and oxygen atoms, dissociating the molecule. For carbon monoxide to survive and accumulate, the gas must be shielded from radiation, typically by dust. But dust itself is made of heavy elements and shouldn't be abundant in the early universe either. It's a chicken and egg problem. You need dust to protect carbon monoxide, but you need multiple generations of stars to make dust, and those generations need time we don't think was available. Webb has also unveiled unexpected details about the morphology of high redshift galaxies. When Hubble observed distant galaxies, they appeared as small, irregular blobs. This was partly due to Hubble's resolution limits, but it also seemed consistent with theoretical predictions that early galaxies were chaotic and unstructured. Webb's sharper vision reveals that many of these galaxies actually have well-defined structures: bars, spiral arms, bulges, and disks. These are features we associate with mature galaxies that have settled into dynamical equilibrium. A galactic bar, for instance, is a linear structure of stars cutting through the center of a spiral galaxy. Bars form through gravitational instabilities when a galaxy's disk becomes massive enough. They're incredibly efficient at funneling gas toward the galactic center, feeding both star formation and the central black hole. Our own Milky Way has a bar, and we thought it took billions of years to develop. Yet Webb is showing us barred galaxies when the universe was only 20% of its current age. The presence of these structures implies that the early universe wasn't just forming stars rapidly. It was also organizing those stars into coherent dynamical systems with remarkable speed. Gravitational interactions must have been extremely efficient, or there were processes at work that accelerated the evolution from chaos to order. Some simulations suggest that gas-rich mergers in the early universe could have rapidly built up massive disks and triggered bar formation, but testing these ideas requires more observations. Webb's spectroscopic capabilities are revealing another layer of complexity in the chemical composition of early galaxies. Different elements have different nucleosynthetic origins. For example, nitrogen can be produced in intermediate mass stars through the cyanose cycle, while elements like magnesium and silicon come from massive stars that explode as core-collapse supernovas. By measuring the relative abundances of these elements, astronomers can infer the stellar populations responsible for enriching the gas. What's puzzling is that some early galaxies show abundance patterns that don't match any single stellar population model. The nitrogen-to-oxygen ratio, for instance, varies widely among galaxies of similar ages and masses. This suggests that the initial mass function, the distribution of stellar masses at birth, might have been different in the early universe, favoring more massive stars in some environments and lower mass stars in others. Alternatively, the timescales for different enrichment processes might have overlapped in complex ways. There's also the question of population 3 stars again, but with a new twist. Some theoretical models predict that these first stars could have been extraordinarily massive, hundreds or even thousands of times the mass of the Sun. Such behemoths would burn through their nuclear fuel in less than 1 million years, then collapse into black holes through a process called direct collapse. They wouldn't explode as supernovas. They'd simply vanish into event horizons, taking most of their mass with them. If significant numbers of these supermassive stars formed, they could explain the presence of massive black holes in the early universe without requiring long growth periods. But they'd also produce very little chemical enrichment, since their material never gets expelled into space. Webb hasn't directly detected any population 3 stars. They're simply too faint and too rare, but the patterns of chemical enrichment and black hole masses it's observing might be indirect evidence of their existence. Another frontier Webb is exploring is the epoch of first light, the moment when the very first stars ignited and ended the cosmic dark ages. This transition wasn't instantaneous or uniform. Different regions of the universe lit up at different times, creating a patchwork of ionized bubbles expanding into the neutral hydrogen fog. As these bubbles grew and merged, they eventually overlapped, completing the reionization process. Webb is mapping these ionized bubbles by studying Lyman alpha emission, a specific wavelength of light emitted by hydrogen when electrons transition between energy levels. Neutral hydrogen absorbs Lyman alpha photons, so regions where we see strong Lyman alpha emission must be ionized. By measuring the size and distribution of these regions, astronomers can reconstruct the timeline and topology of reionization. The data suggests that reionization was more complex than simple models predicted. Some regions ionized very early, within 400 million years of the Big Bang, while others remained neutral much longer. This patchiness implies that the sources of ionizing radiation, early stars and galaxies, were unevenly distributed, clustering in dense regions while leaving voids relatively untouched. Understanding this distribution tells us about the underlying dark matter structure and the efficiency with which gas fell into dark matter halos. Webb has also observed something called damped Lyman alpha systems, dense clouds of neutral hydrogen that absorb background light from quasars. These systems are thought to be the progenitors of galaxies, reservoirs of gas that will eventually collapse and form stars. By studying their properties, mass, metallicity, kinematics, we learn about the raw materials available for galaxy formation and how those materials evolve over time. What's striking is that even these pristine gas clouds show signs of chemical enrichment at high redshifts. They're not completely metal-free. This suggests that the first stars and supernovas were effective at dispersing their products over large volumes, enriching gas that hadn't yet formed into galaxies. It's a form of cosmic pollution, where the byproducts of stellar death spread far beyond their birthplaces. Let's consider Webb's observations of intermediate redshift galaxies, those at redshifts between 2 and 6, corresponding to when the universe was between 1 and 3 billion years old. This epoch, sometimes called cosmic noon, is when the universe was at its most active in terms of star formation. More stars formed during this period than at any other time in cosmic history. It's the adolescence of the universe, a time of rapid growth and transformation. Webb is revealing that galaxies at cosmic noon were incredibly diverse. Some were compact and intensely star-forming, packing enormous amounts of activity into small volumes. These are often called starburst galaxies, and they can form stars at rates hundreds of times higher than the Milky Way. Others were more sedate, forming stars steadily over longer periods. Still others were already quiescent, having somehow shut down their star formation despite being relatively young. The variety suggests that galaxy evolution isn't a single pathway but a branching tree with multiple routes and outcomes. Environmental factors play a role. Galaxies and dense clusters evolve differently than isolated galaxies. Mergers and interactions can trigger bursts of star formation or, paradoxically, shut it down by heating gas or expelling it from the galaxy. Internal factors matter too: the mass of the central black hole, the angular momentum of the gas, the efficiency of supernova feedback. Webb's ability to measure stellar masses, gas masses, star formation rates, and black hole masses for individual galaxies at these redshifts is allowing astronomers to construct detailed evolutionary tracks. They can see which galaxies are growing primarily through star formation versus mergers, which are accumulating gas versus losing it, which are building up their bulges versus their disks. It's like having census data for the entire galactic population across billions of years. One particularly intriguing class of objects Webb has studied are sub-millimeter galaxies, extremely dusty star-forming galaxies that emit most of their light in the far infrared and sub-millimeter wavelengths. These galaxies are so obscured by dust that they're nearly invisible in optical light, but they shine brilliantly in infrared. They're among the most luminous objects in the universe, powered by star formation rates that can exceed 1,000 solar masses per year. Webb's infrared vision is perfect for studying these dust-shrouded behemoths. It can peer through the dust and measure their stellar content, determine their redshifts, and understand what's driving their extreme star formation. Many turn out to be undergoing major mergers, collisions between massive gas-rich galaxies that compress the gas and trigger intense star formation. These mergers might be the ancestors of today's giant elliptical galaxies, massive and red, no longer forming stars. The connection between mergers and galaxy evolution raises questions about how important mergers really are. For a long time, astronomers thought mergers were the primary driver of galaxy growth, with galaxies assembling hierarchically through countless mergers of smaller systems. But Webb's observations suggest that many massive galaxies at high redshift appear relatively undisturbed, without obvious signs of recent mergers. This implies that smooth accretion of gas from the intergalactic medium might be more important than previously thought. Smooth accretion is the process by which galaxies pull in gas from their surroundings through gravity. The gas flows along cosmic filaments, streams of matter connecting galaxies across vast distances. As the gas falls into the galaxy's gravitational well, it heats up, but if it can cool efficiently, it settles into the disk and becomes available for star formation. This process can sustain steady star formation over long periods without the drama of a merger. Webb has detected evidence of these cold gas streams through absorption line studies. When light from a distant quasar passes near a galaxy, the intervening gas absorbs specific wavelengths, leaving imprints in the quasar's spectrum. By analyzing these absorption features, astronomers can map the distribution of gas around galaxies and measure its velocity. Some of this gas is inflowing, some is outflowing, and some is just sitting there in the circumgalactic medium, a diffuse halo surrounding the galaxy. The circumgalactic medium is a reservoir and a battleground. It's where gas from the intergalactic medium meets gas expelled by the galaxy through stellar winds and supernova feedback. The balance between inflow and outflow determines whether a galaxy grows or shrinks, whether it continues forming stars or becomes quiescent. Webb's observations are showing that this balance is delicate and varies from galaxy to galaxy. Another aspect of Webb's mission involves studying gravitational lensing in exquisite detail. Strong gravitational lensing occurs when a massive foreground object, like a galaxy cluster, bends light from a background galaxy so severely that multiple images appear, often in the form of arcs or rings. Webb's resolution allows astronomers to model these lenses with unprecedented precision, determining the distribution of mass in the lensing cluster, including the dark matter. By comparing these mass distributions with the visible matter, stars and gas, we can test our models of dark matter. Does it clump in the way cold dark matter predicts? Are there deviations that might hint at dark matter's properties, like its particle mass or interaction cross-section? So far, observations are broadly consistent with cold dark matter, but there are tantalizing hints of small-scale discrepancies that might indicate more complex physics. Lensing also magnifies background galaxies, allowing Webb to study objects that would otherwise be too faint to detect. Some of the most distant galaxies known were discovered through lensing. The magnification can be factors of 10, 50, even 100, effectively giving us a much larger telescope. Its nature providing us with a free boost in sensitivity. One lensed galaxy Webb observed in detail is a galaxy at redshift 9.1, seen when the universe was about 550 million years old. Thanks to lensing magnification, astronomers could resolve structures within the galaxy as small as 200 light-years across. They identified multiple star-forming clumps, each a site of intense activity. This clumpy structure is characteristic of high redshift galaxies and suggests that star formation in the early universe wasn't uniformly distributed across the galaxy but concentrated in dense pockets. These clumps might be the building blocks of galactic bulges, the dense central regions of spiral galaxies. Simulations suggest that clumps can migrate inward through dynamical friction, a process where gravitational interactions with surrounding stars slow them down, causing them to spiral toward the center. Over time, they merge, forming a bulge. Webb's observations provide direct evidence of this process in action. There's also the phenomenon of cosmic rays, high-energy particles that zip through space at nearly the speed of light. Cosmic rays are mostly protons, but they include heavier nuclei and even electrons and positrons. They're produced in supernova remnants, pulsars, and possibly in the jets of active galactic nuclei. When cosmic rays interact with gas and dust, they produce gamma rays and other forms of radiation that Webb can detect indirectly. Cosmic rays play multiple roles in galaxy evolution. They provide pressure support, helping to prevent gas from collapsing and forming stars too efficiently. They can drive galactic winds, launching gas out of the galaxy. They also regulate the chemistry of the interstellar medium, ionizing molecules and atoms. Understanding cosmic ray populations in distant galaxies is challenging, but Webb's spectroscopic observations of high-energy emission lines are providing clues. Let's turn our attention to the role of active galactic nuclei, or AGN, in shaping galaxy evolution. An AGN is powered by a supermassive black hole accreting matter, and the energy released can be enormous, sometimes outshining the entire host galaxy. This energy affects the surrounding gas, heating it, ionizing it, and in some cases, expelling it from the galaxy entirely. This process, called AGN feedback, is thought to be crucial for regulating star formation in massive galaxies. Webb has observed AGN across a wide range of redshifts, from the nearby universe to the earliest epochs. One surprising finding is that many high redshift AGN are surrounded by intense star formation rather than being shut down by feedback. This suggests that AGN feedback might be less efficient in the early universe, or that the gas supplies were so abundant that even vigorous feedback couldn't completely halt star formation. There's a delicate interplay between the black hole and its host galaxy. As the black hole grows by accreting gas, it releases energy that can either promote or suppress star formation depending on how that energy couples to the gas. If the energy heats the gas without expelling it, the gas might become more turbulent, which can actually trigger star formation in dense regions. If the energy drives a powerful outflow, it can remove gas from the galaxy, starving future star formation. Webb has detected these outflows in action, observing gas moving at speeds of thousands of kilometers per second away from AGN. The mass outflow rates can exceed the star formation rate, meaning the galaxy is losing gas faster than it's turning it into stars. Over time, this will quench star formation, transforming a star-forming galaxy into a quiescent one. This might be how massive elliptical galaxies became red and dead. Another topic Webb is illuminating is the nature of dust grains themselves. Dust isn't just dirt, it's composed of specific minerals and compounds that form in the atmospheres of dying stars and in supernova ejecta. Silicates, graphite, amorphous carbon, polycyclic aromatic hydrocarbons, each has a distinct spectral signature. Webb's spectrographs can identify these signatures, telling us not just that dust is present but what kind of dust and in what proportions. Different dust compositions have different properties. Silicate grains are efficient at absorbing ultraviolet and optical light, while carbonaceous grains emit strongly in the infrared. The ratio of silicate to carbon dust tells us about the types of stars that produce the dust. Asymptotic giant branch stars, for example, produce more silicates, while supernovas produce more carbon. By measuring dust composition in distant galaxies, we're learning about their stellar populations in a completely independent way from traditional spectroscopy. Webb has also discovered dust at surprisingly high redshifts, in galaxies where the dust shouldn't have had time to form. This is yet another piece of the puzzle suggesting that the early universe was more efficient at processing material than we expected. It's possible that supernovas in the early universe produced more dust per event, or that dust grains grew faster by accreting atoms from the gas phase. There's an interesting connection between dust and planet formation. In our solar system, dust grains in the protoplanetary disk stuck together, gradually growing into pebbles, boulders, and eventually planets. The composition of that dust determined the composition of the planets. Rocky planets like Earth are made from silicate dust, while gas giants like Jupiter formed farther out where ices could condense. By studying dust in protoplanetary disks around other stars, Webb is revealing the initial conditions for planet formation in diverse environments. One system Webb observed in detail is a young star with a disk showing gaps and rings, structures carved by forming planets. By measuring the dust properties in different parts of the disk, astronomers could infer that planets of various sizes were forming at different distances from the star. Closer in, where temperatures are higher, the dust is dominated by silicates. Farther out, where it's cooler, ice-coated grains are present. This temperature gradient creates different planetary compositions at different orbital distances. Webb's studies of exoplanet atmospheres are revealing chemical diversity that mirrors the diversity of planetary system architectures. Some hot Jupiters have atmospheres rich in water vapor and carbon monoxide, while others show evidence of exotic clouds made of vaporized rock. Super-Earths, planets larger than Earth but smaller than Neptune, display a range of atmospheric compositions from hydrogen-dominated to nitrogen-dominated to potentially even oxygen-rich. The search for biosignatures, chemical indicators of life, is one of Webb's most exciting applications. Oxygen and methane together, for instance, are a potential biosignature because these gases react with each other chemically. Their coexistence in an atmosphere requires a continuous source, and on Earth, that source is life. Plants produce oxygen through photosynthesis, while microbes produce methane. Finding both gases in an exoplanet's atmosphere wouldn't be definitive proof of life, but it would be tantalizing. Webb hasn't yet detected such a biosignature, and realistically, it might not be sensitive enough to do so for small rocky planets around Sun-like stars. Those planets are faint, and their atmospheric signals are weak. But Webb is paving the way for future missions specifically designed for biosignature detection, missions like the Habitable Worlds Observatory that NASA is planning for the 2040s. Let's consider the broader implications of what Webb is teaching us about the universe's habitability. Every discovery about planetary systems, about the distribution of water and organic molecules, about the conditions in protoplanetary disks, informs our understanding of how common Earth-like planets might be. If the ingredients for life are widespread, if planetary systems form readily, if habitable zones are common, then life might be common too. Conversely, if planet formation is a delicate process requiring specific conditions, if habitable planets are rare, if the chemical pathways to life are fraught with obstacles, then we might be alone or at least very isolated. Webb's data is helping to quantify these probabilities, moving the question of life's prevalence from speculation to science. There's a statistical framework called the Drake equation that attempts to estimate the number of communicative civilizations in the galaxy. It factors in the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction on which life arises, the fraction that develops intelligence, and so on. Webb's observations are refining several of these terms, particularly those related to planetary systems and habitable zones. Beyond the search for life, Webb is also contributing to our understanding of cosmic timescales. The universe is 13.8 billion years old, a number determined with increasing precision over the years. But within that time span, different processes operate on different timescales. Star formation takes millions of years. Galaxy mergers take hundreds of millions to billions of years. The evolution of planetary atmospheres can take billions of years. Understanding these timescales is crucial for interpreting observations. When we see a galaxy in a particular state, we're seeing a snapshot of an ongoing process. Is it at the beginning, middle, or end of that process? How long will it remain in this state before transitioning to the next? Webb's ability to observe large samples of galaxies at different epochs allows astronomers to construct evolutionary sequences, piecing together the full story from individual snapshots. This is analogous to trying to understand human aging by observing a crowd of people. You see infants, children, adults, and elderly individuals, each at a different stage. By studying the full range, you can infer the progression even though you're not watching any single person age. Similarly, by studying galaxies across cosmic time, we infer the evolutionary pathways even though we can't watch individual galaxies evolve. Webb is also revealing the intricate relationship between galaxies and their surrounding cosmic web, the vast network of filaments and voids that defines the large-scale structure of the universe. This cosmic web emerged from tiny density fluctuations in the early universe, amplified by gravity over billions of years. Galaxies aren't randomly scattered through space. They trace this underlying structure, clustering along filaments like beads on invisible strings. What Webb has discovered is that this structure was already surprisingly well developed at high redshifts. Galaxies in the early universe weren't isolated islands, but were already part of interconnected networks. Some resided in protoclusters, the ancestors of today's massive galaxy clusters, regions where dozens or hundreds of galaxies were assembling in close proximity. These protoclusters are cosmic hothouses where interactions are frequent, gas is abundant, and evolution proceeds at an accelerated pace. The environmental effects on galaxy evolution are profound. Galaxies in dense regions experience ram pressure stripping, where the hot intracluster gas literally blows away the cold gas from the galaxy as it moves through the cluster. Without cold gas, star formation ceases. Galaxies can also undergo harassment, repeated high-speed encounters with neighbors that gravitationally disturb them, heating their stellar disks and transforming their morphologies. Over time, spiral galaxies entering clusters can become elliptical or lenticular, stripped of gas and structure. Webb has observed galaxies caught in these transformations, objects in transition between being actively star-forming and becoming quiescent. These galaxies often show disturbed morphologies, asymmetric structures, or tidal tails, long streams of stars pulled out by gravitational interactions. They're cosmic accident scenes, frozen moments, and violent processes that will fundamentally alter the galaxies involved. There's also the phenomenon of jellyfish galaxies, aptly named for the long tendrils of gas and young stars streaming behind them as they plow through the intra-cluster medium. The ram pressure strips away their gas in real time, creating spectacular tails that can extend for hundreds of thousands of light years. Within these tails, stars continue to form, creating chains of bright knots visible in Webb's images. These are stars born in exile, forming far from their parent galaxy as the gas from which they condensed is forcibly removed. What makes these observations particularly valuable is that they allow us to study galaxy transformation mechanisms in action rather than inferring them from indirect evidence. We can measure the gas stripping rates, the star formation occurring in the tails, the chemical composition of the stripped material. Each observation refines our models of how environment shapes galactic destiny. Webb has also turned its attention to galaxy clusters themselves, massive gravitationally bound systems containing hundreds or thousands of galaxies along with enormous quantities of hot gas and dark matter. These clusters are the most massive structures in the universe that have had time to gravitationally collapse and reach equilibrium. They're cosmic laboratories for studying dark matter, plasma physics, and galaxy evolution under extreme conditions. The hot intracluster gas, heated to tens of millions of degrees by gravitational compression and shocks from merging subclusters, emits X-rays that other telescopes detect. But Webb observes the aftermath of processes that this hot gas enables. When the gas cools and condenses, it can rain down onto the central galaxy, fueling both star formation and black hole growth. Webb has detected this cool gas in filamentary structures within cluster cores, providing direct evidence of the cooling flow process that has been theoretically predicted for decades. Some clusters show evidence of AGN feedback on cluster scales. The supermassive black hole in the central galaxy produces jets that inflate enormous bubbles in the hot gas, cavities hundreds of thousands of light years across. These bubbles prevent the gas from cooling too rapidly, regulating both the growth of the central galaxy and the overall thermal state of the cluster. It's a self-regulating system where the black hole acts as a thermostat, maintaining the cluster in a delicate balance. Webb's observations of high redshift protoclusters are showing that these structures were already massive enough to contain substantial amounts of hot gas, though not as hot or as dense as in today's clusters. The transition from protocluster to mature cluster involves numerous mergers and the gradual accumulation of gas, processes that Webb is documenting across cosmic time. Let's shift to an entirely different scale, the centers of galaxies. Galactic nuclei are extraordinary environments where stellar densities can reach millions of stars per cubic light-year, where supermassive black holes dominate the gravitational potential, and where processes operate at extremes of energy and density. Webb has resolved the central regions of nearby galaxies with unprecedented clarity, revealing complex structures invisible to previous telescopes. In the Milky Way's center, which we can study in more detail than any other galactic nucleus, Webb has observed the dense stellar cluster surrounding Sagittarius A-, our central black hole. This cluster contains massive young stars whose presence is puzzling. How did they form so close to a supermassive black hole where tidal forces should prevent star formation? One possibility is that they formed farther out and migrated inward. Another is that they formed in a massive gas disk that briefly existed close to the black hole. Webb's observations of other galactic nuclei might reveal whether similar stellar populations are common, providing clues to their origin. Webb has also studied nuclear star clusters in other galaxies, finding that many contain multiple generations of stars with different ages and metallicities. This suggests episodic formation, with star formation turning on and off over millions of years. What triggers these episodes? Possibly gas infall events, when material from the outer galaxy makes its way to the center, or interactions with satellite galaxies that disturb the nuclear region. Another feature Webb is investigating is nuclear rings, circular or elliptical structures of intense star formation surrounding many galactic centers. These rings form where gas accumulating in the inner galaxy encounters resonances in the gravitational potential, locations where the orbital periods of gas clouds create standing wave patterns. The gas piles up at these resonances, reaching densities high enough to trigger star formation. Our own galaxy has such a ring, though it's not easily visible due to our location within the disk. Webb's infrared capabilities allow it to penetrate the dust that obscures many galactic centers, revealing the full extent of star formation and AGN activity. Some galaxies host both, a supermassive black hole actively accreting and a surrounding starburst. Disentangling the contributions of each to the total luminosity requires careful spectroscopy, measuring emission lines that trace ionized gas around the black hole versus absorption features from stars in the starburst. There's a class of galaxies called liners, for low ionization nuclear emission line regions, that show unusual spectral signatures suggesting weak AGN activity or possibly stellar processes. Webb's detailed spectra are helping to resolve the nature of these objects, determining whether they host low luminosity AGN, unusually hot stars, or some combination. The answer has implications for how we count AGN and for understanding the low activity phases of black hole growth. Webb has also observed tidal disruption events, rare occurrences when a star ventures too close to a supermassive black hole and is torn apart by tidal forces. Half the star's material is flung into space while the other half spirals into the black hole, creating a temporary flare of emission across multiple wavelengths. Webb can observe the infrared emission from dust that forms in the expanding debris, providing insights into the physics of these violent events. Moving to yet another frontier, Webb is studying the epoch around redshift 2 to 3, corresponding to roughly 10 to 11 billion years ago, when the universe was in a particularly interesting phase. This was after the peak of cosmic star formation but before the universe settled into its current relatively quiescent state. During this epoch, massive galaxies were transitioning from star-forming to quiescent, dark energy was beginning to dominate the universe's energy budget, and the intergalactic medium was becoming more metal-enriched. Webb's observations at these redshifts are capturing galaxies in mid-transition, objects that are reducing their star formation rates but haven't completely shut down. These transitioning galaxies often have green colors, intermediate between the blue of star-forming galaxies and the red of quiescent ones, earning them the nickname Green Valley Galaxies. Understanding what drives galaxies through the Green Valley, whether it's AGN feedback, environmental processes, or simply exhaustion of gas supplies, is a major goal of modern astrophysics. Some Green Valley galaxies show signs of post-starburst activity, meaning they recently underwent an intense burst of star formation that has since ceased. The spectra show strong Balmer absorption lines from A-type stars, which are the remnants of massive stars that formed in the burst but have now aged. These galaxies might have experienced a major merger that consumed all their gas in a brief period of intense star formation, after which they became quiescent. Webb is also revealing details about the circumgalactic medium at these intermediate redshifts, the diffuse gas surrounding galaxies. This material is difficult to observe directly because it's too hot and diffuse to emit much radiation. But when background quasars shine through it, the gas absorbs specific wavelengths, leaving absorption signatures in the quasar spectra. By studying these absorption systems, astronomers map the distribution and properties of circumgalactic gas. The circumgalactic medium serves multiple functions. It's a reservoir of gas that can fuel future star formation if it cools and flows into the galaxy. It's a repository for material ejected by supernovas and stellar winds, enriched with heavy elements. It's also a boundary layer where gas from the intergalactic medium slows down and begins to join the galaxy's gravitational sphere of influence. Understanding its structure and dynamics is crucial for understanding galaxy evolution as a whole. Webb has detected evidence of co-rotating circumgalactic gas, material that shares the galaxy's angular momentum and orbits in the same direction as the galaxy's disk. This suggests the gas was accreted smoothly along cosmic filaments rather than from random directions. Other galaxies show circumgalactic gas with little net rotation, suggesting a more chaotic accretion history involving mergers or gas accretion from multiple directions. Let's explore another domain where Webb is making contributions, the study of variable phenomena. The universe isn't static. Objects change brightness over time for various reasons. Stars pulsate, supernovas explode, AGN flicker, Gravitational lensing events occur when compact objects pass in front of background sources. Webb can revisit the same patch of sky multiple times, creating time-domain observations that reveal these changes. One application is searching for supernovas in distant galaxies. By comparing images taken months or years apart, astronomers can identify new bright points that appeared, supernovas. Webb's infrared sensitivity is particularly valuable for finding supernovas at high redshifts, where their light has been redshifted into Webb's wavelength range. These distant supernovas are crucial for measuring cosmic distances and refining our understanding of dark energy. Webb has also observed AGN variability, the flickering of active galactic nuclei as the accretion flow onto the black hole fluctuates. This variability occurs on timescales ranging from hours to years, depending on the size of the emission region. By studying variability patterns, astronomers can map the structure of the material surrounding the black hole, using a technique called reverberation mapping where light travel time delays between different emission regions reveal their spatial arrangement. Gravitational microlensing is another time-variable phenomenon Webb can study. When a compact object like a star or planet passes in front of a more distant source, its gravity bends and magnifies the background light, creating a temporary brightening. These events are unpredictable and brief, but when Webb happens to observe one, the detailed light curve can reveal the mass and properties of the lensing object. There's also the study of periodic variables like Cepheid variable stars, which Webb has observed with exceptional precision. These stars pulsate regularly, expanding and contracting with periods ranging from days to months. The period is directly related to the star's intrinsic luminosity through a well-established relationship, making Cepheids invaluable distance indicators. Webb's infrared observations are less affected by dust extinction than optical observations, providing more accurate distance measurements. Another class of variable stars are eclipsing binaries, systems where two stars orbit each other and periodically pass in front of one another from our perspective. By analyzing the light curves, how the brightness changes during eclipses, astronomers can determine the stars' sizes, masses, and orbital parameters with remarkable precision. Webb has observed eclipsing binaries in distant galaxies and star clusters, providing fundamental stellar properties that inform models of stellar evolution. Let's consider the role of simulations in interpreting Webb's observations. Modern cosmological simulations are computational marvels, evolving billions of particles representing dark matter and gas from shortly after the Big Bang to the present day. These simulations incorporate the physics of gravity, hydrodynamics, star formation, supernova feedback, black hole growth, and AGN feedback. They're tested against observations, with parameters adjusted until the simulated universe resembles the real one. Webb's observations are providing stringent new tests for these simulations. The early massive galaxies, the rapid chemical enrichment, the abundance of supermassive black holes, these weren't predicted by simulations, at least not by the simulations that existed before Webb. Now, theorists are scrambling to adjust their models, tweaking parameters, incorporating new physics, and running new simulations to see if they can reproduce what Webb is seeing. Some adjustments are straightforward. Perhaps the efficiency of star formation was higher in the early universe. Perhaps supernova feedback was less effective at expelling gas. Perhaps black holes grew more efficiently through mergers or direct collapse mechanisms. But other aspects might require more fundamental changes to our models, possibly involving modifications to our understanding of dark matter, dark energy, or even the cosmological parameters themselves. The process is iterative. Observations constrain models, which make new predictions, which are tested against new observations. When discrepancies arise, models are revised. Over time, this process converges toward theories that accurately describe reality. Webb is accelerating this process by providing observations that existing models struggle to explain, forcing rapid theoretical development. One particular challenge for simulations is reproducing the morphological diversity of galaxies. It's relatively easy to grow massive galaxies in simulations. Just let dark matter halos accrete material and form stars. But getting the detailed structure right, with spiral arms, bars, bulges, and disks all appearing at the right times and with the right proportions, is much harder. The physics of angular momentum transport, turbulence, magnetic fields, and star formation on subgalactic scales is complex and computationally expensive to model. Webb's high-resolution images of distant galaxies are providing new benchmarks for simulations. Theorists can now compare not just the masses and luminosities of simulated galaxies but also their morphologies, sizes, and internal structures. When simulations produce galaxies that look wrong, too compact, too smooth, with the wrong color gradients, it indicates missing or incorrect physics that needs to be addressed. There's also the challenge of simulating the multi-phase interstellar medium, the coexistence of cold molecular clouds, warm ionized gas, and hot plasma within galaxies. These phases interact in complex ways, with supernova shocks creating hot gas that cools and condenses into clouds, which then form stars that explode and create more hot gas. Webb's observations of emission lines from different phases provide constraints on these models. Let's turn our attention to a cosmic mystery that Webb is helping to address: the nature of dark matter on small scales. While dark matter's existence is well established through its gravitational effects on large scales, its behavior on smaller scales is less certain. Cold dark matter predicts a hierarchy of structures, with large halos containing numerous smaller subhalos. But observations suggest there might be fewer small-scale structures than predicted, a discrepancy called the missing satellites problem. Webb can detect faint dwarf galaxies at large distances, galaxies that might reside in small dark matter halos. By counting how many such galaxies exist and measuring their properties, astronomers can test predictions of dark matter models. If cold dark matter is correct, there should be abundant small halos, many containing dwarf galaxies. If the observations show fewer dwarfs than expected, it might indicate that dark matter is warmer than assumed, or that feedback processes are more effective at preventing star formation in small halos. Another small-scale test involves gravitational lensing. Dark matter substructure within lensing galaxies should create subtle distortions in the images of background sources. Webb's sharp vision might detect these subtle effects, providing direct evidence of dark matter clumps too small to contain visible galaxies. Early results are intriguing but not yet conclusive, and more observations are needed. There's also the question of dark matter's possible self-interactions. Most models assume dark matter particles only interact gravitationally, passing through each other and through ordinary matter without friction or collision. But some theories propose that dark matter particles can scatter off each other through a weak dark force, analogous to electromagnetism but much weaker. Such interactions would affect the density profiles of dark matter halos, making their cores less dense. Webb's observations of galaxy rotation curves and lensing profiles can test these predictions. Moving back to larger scales, Webb is contributing to measurements of the cosmic distance ladder, the series of techniques used to measure distances across the universe. Each rung of the ladder depends on the previous one, so errors accumulate. The ladder starts with parallax measurements to nearby stars, extends through Cepheid variables to more distant galaxies, and culminates with Type Ia supernovas reaching across billions of light-years. Webb's infrared observations of Cepheids are improving the precision of distance measurements to galaxies that host Type Ia supernovas. This reduces uncertainties in the Hubble constant and helps address the Hubble tension. The more precise our distances, the better we can constrain the universe's expansion history and the properties of dark energy. There's also a completely independent distance measurement technique using gravitational wave observations. When LIGO detects the merger of two neutron stars or black holes, the gravitational wave signal encodes information about the system's intrinsic luminosity in gravitational waves. By comparing this to the observed amplitude, the distance can be calculated without needing the cosmic distance ladder. If the merger has an electromagnetic counterpart that Webb can observe, the object's redshift can be measured, providing a direct measurement of the Hubble constant at that distance. These multi-messenger observations, combining gravitational waves with electromagnetic radiation, are opening entirely new avenues for cosmology. Webb's role is to provide the electromagnetic follow-up, identifying the host galaxy, measuring its redshift, and characterizing the environment where the merger occurred. Let's explore Webb's observations of our own solar system's outer reaches. The Kuiper Belt, a region of icy bodies beyond Neptune's orbit, contains remnants from the solar system's formation. These objects are preserved in deep freeze, retaining the primordial composition of the solar nebula. Webb has observed several Kuiper Belt objects, measuring their surface compositions and detecting volatiles like methane, carbon monoxide, and nitrogen. One surprising finding is the diversity of surface properties among Kuiper Belt objects. Some are bright and icy, dominated by water ice and frozen volatiles. Others are dark and reddish, covered with organic compounds called tholins produced by radiation processing of surface ices. This diversity suggests different formation locations or evolutionary histories, with some objects experiencing more exposure to cosmic rays and solar radiation than others. Webb has also observed comets, those spectacular visitors from the outer solar system that develop tails when they approach the Sun. As a comet's ices sublimate, they release gas and dust, creating the coma and tail. Webb's spectroscopy can identify specific molecules in the coma, including water, carbon dioxide, carbon monoxide, methane, and more complex organics. Each comet has a slightly different composition, reflecting the conditions in the part of the solar nebula where it formed. One comet Webb studied showed an unusually high abundance of carbon monoxide relative to water, suggesting it formed in a very cold region where carbon monoxide could condense. Another showed evidence of complex organic molecules including formaldehyde and ethanol, the building blocks for more sophisticated chemistry. These observations inform our understanding of the chemical inventory delivered to the early Earth by cometary impacts, possibly contributing to the origin of life. Webb has even observed asteroids, rocky bodies primarily located in the asteroid belt between Mars and Jupiter. While asteroids are warmer than Kuiper Belt objects and lack significant ice, Webb's thermal infrared observations can determine their surface temperatures, which depend on their size, composition, and rotation rate. By observing asteroids at different phases of their rotation, astronomers can construct shape models and study surface heterogeneity. Some asteroids show evidence of hydrated minerals, silicates with water molecules incorporated into their crystal structure. These minerals form when liquid water interacts with rock, suggesting that some asteroids experienced aqueous alteration, possibly due to heat from radioactive decay melting internal ice. Webb's detection of these minerals helps us understand the distribution of water in the early solar system. There's also the study of asteroid families, groups of asteroids with similar orbits that are fragments from ancient collisions. Webb can measure the spectral properties of family members, determining whether they all have similar compositions or if the parent body was differentiated, with a rocky mantle and metallic core. Collisions can expose interior material, allowing us to study the internal structure of asteroids indirectly. Let's return to the cosmic scale and consider Webb's role in studying the large-scale structure of the universe. The distribution of galaxies isn't random but follows a pattern set by the initial density fluctuations in the early universe. These fluctuations, imprinted during inflation, grew through gravitational instability into the cosmic web we see today. Webb can map this structure by conducting deep surveys over wide areas, identifying galaxies and measuring their redshifts to determine their three-dimensional positions. These surveys reveal how structure has evolved over cosmic time, showing how filaments grew, how clusters assembled, and how voids expanded. Comparing these observations to predictions from cosmological models tests our understanding of dark matter, dark energy, and the initial conditions of the universe. One particularly interesting feature is the existence of cosmic voids, vast regions containing few galaxies. These voids aren't completely empty. They contain some diffuse gas and a few dim galaxies, but their average density is far below the cosmic mean. Voids expand over time as dark energy accelerates the universe's expansion, and their growth rate is sensitive to the properties of dark energy. Webb's observations of galaxies on void edges and within voids provide data for testing dark energy models. There are also cosmic walls and filaments, regions where galaxies are densely concentrated. These structures can extend for hundreds of millions of light years, forming the boundaries between voids. Webb has observed galaxies within these structures at various redshifts, tracking how filaments evolve and how galaxies within them interact and merge. Another aspect of large-scale structure is the phenomenon of baryon acoustic oscillations, subtle ripples in the distribution of galaxies caused by sound waves in the early universe. Before recombination, when the universe became transparent, pressure waves propagated through the coupled photon-baryon fluid, creating regions of slightly higher and lower density. After recombination, these pressure waves froze as density variations that seeded galaxy formation. The scale of these oscillations, about 500 million light-years in the present-day universe, provides a standard ruler for measuring cosmic distances. By mapping galaxy distributions and identifying this characteristic scale, astronomers can measure how the universe has expanded over time, providing another constraint on dark energy. Webb's spectroscopic surveys contribute to this effort by measuring precise redshifts for large numbers of galaxies. Let's consider Webb's contributions to understanding the thermal history of the universe. After recombination, when atoms formed and the universe became transparent, the cosmic microwave background photons began a long journey through space. As the universe expanded, these photons were redshifted to longer wavelengths and cooler temperatures. But the history wasn't entirely smooth. Reionization heated the intergalactic medium, and later, structure formation created regions of varying temperature. Webb can study this thermal history by observing the Sunyaev-Zeldovich effect, where cosmic microwave background photons passing through hot gas gain energy through inverse Compton scattering. This creates characteristic distortions in the microwave background spectrum that other telescopes detect. Webb's role is to identify and characterize the galaxy clusters responsible for these distortions, measuring their masses and gas properties. Another thermal signature comes from the temperature of the intergalactic medium itself, which can be inferred from the widths of absorption lines in quasar spectra. Hotter gas has more thermal broadening, making absorption lines wider. By measuring these widths at different redshifts, astronomers reconstruct the thermal history of intergalactic gas, learning when and how it was heated. Webb has also observed the cosmic infrared background, the cumulative light from all sources throughout cosmic history that has been redshifted into the infrared. This background contains contributions from the first stars, from dust-obscured galaxies, from AGN, and from other sources. By carefully subtracting foreground sources and isolating the diffuse background, astronomers can study the integrated emission from epochs and objects too faint to detect individually. Fluctuations in this background reveal clustering of the sources responsible. If the first stars formed in small halos scattered throughout space, the background would be relatively smooth. If they formed in larger, more clustered structures, the background would show more pronounced fluctuations on certain angular scales. Webb's measurements of these fluctuations constrain models of early structure formation. There's also the study of the metagalactic radiation field, the diffuse UV and optical light that permeates intergalactic space, produced primarily by galaxies and quasars. This radiation ionizes the intergalactic medium and affects the thermal state of gas clouds. Webb can study this radiation field indirectly through its effects on distant objects. Let me now address something profound about what all these Webb observations collectively represent. We're witnessing the universe reveal itself in ways that consistently surprise us, that challenge our models, that force us to think more creatively about cosmic processes. Each discovery from Webb isn't just a data point, it's a hint that reality is richer and more complex than our theories currently capture. The scientific method thrives on this tension between observation and theory. Theories guide what we observe, but observations ultimately determine which theories survive. Webb is providing observations that many theories didn't predict, creating productive tension that drives scientific progress. This is exactly what we should hope for from a revolutionary instrument, not confirmation of everything we already believed, but revelations that expand our understanding.